you very much, everybody. Okay, so, hi everybody. My name is Idan Shalom. I'm working in hibernating rhinos for more than 2 years now. As part of my job, we develop a database that's called RavenDB. Now, one of the biggest topics that I encountered when develop a system that used those databases is the way to make the system as a distributed way, develop the system as a distributed way. So this is what I want to talk to you about. Distributed system, when democracy and computer science come together, and what does it mean, democracy, right, in computer science. So what is on the menu today? I'm going to talk about, obviously, about distributed systems. I'm going to show you a little bit of the challenges that we can encounter when we develop those systems. And I want to show you in the end how Raft algorithm can help me to achieve a safety and reliable system that I want to develop. So what is a distributed system? One of the definitions that I encounter when I have a research about the distributed system is that distributed system is a collection of independent computers that appear to its user as a single system. So what does it mean? You can take, for example, Facebook or Google, that for us, the user, sometimes seems like one big system, but in the back end, in the background, it's independent of computers that work together to achieve one goal, to give us the data or to give us just the list of our friends in the Google, in the Facebook. So, to define a system as a distributed system, the system must have three main characteristics. So one of them is concurrency. What does it mean? It means that I can work on my computer, and you can work on yours, and everything will work fine. The other one is independent failure. It means that if less of the majority of the nodes that working on the cluster is failing, the system will work just fine and won't throw something like I can't connect to the system anymore. And the last one, all the computer or nodes in our system are not sharing a global clock. It means that if I want to synchronize between all those systems, they must be with messages on the network. So think about all the problems that we can encounter when we have a system that cannot synchronize by clock. If I have a clock, I just can say to my nodes in Cycle, please update yourself in 4 o'clock, and everybody will synchronize themselves as a 4 o'clock, and everything will be fine. Now, like you can see here, we have many challenges that must be addressed in the distributed systems, like heterogeneity, transparency, openness, concurrency, security, stability. And if we take, for example, just the heterogeneity, all the systems can have different hardware, like computers, like phones, like tablets, different programming languages, like Java, Python, C#, and more and more. We can even have different operation system. We can have like Windows, like Linux. All those things must be addressed in the distributed system to achieve a reliable system that can work for many time and not to have problems. There is another theory in the distributed system that's called CAP theorem. So the CAP theorem states that it is impossible for a distributed data store to provide more than 2 of the following 3 guarantees. So you have consistency, that we want to get the most recent writes, like we write something, when we read it, we want to be most updated data that I can receive. Availability, that every request get a response. We don't guarantee that it will be the most updated, but we'll get a response. And of course, partition tolerance, it means that even if we have a partition network or messages, the system could work and not have problems. Now, let me tell you a story. One day one day you wake up in the afternoon, right? You have a good life, so you wake up in the afternoon, and you have a good, very, very good idea for a movie script. You call to a friend, so enthusiastic, and you call to a friend and say, hey man, I have a good idea to have a movie script for a movie. And so, wow, yeah, I'm having too. And you're starting to talk about the movie script, and he telling you his ideas, and you're telling yours, and you're writing something down, and then your phone dies. And you don't have a charger by yourself, so you found yourself in a partition network. So, because you're so enthusiastic to finish your script, you're writing and writing and writing again, but you need to think that your friend is writing something too. And then your spouse comes to you and says to you, hey honey, what are you writing so much? Tell them, I have a good idea for a script. Can I see what you're writing? Now you have two options. One, you can give her the script, even if it's not done because your friend is writing two, you are writing one, and you can choose to be available and to give her the script, or you can say to her, honey, I'm sorry, it's not done yet, and to be consistent because it's not the most updated data that you can have. So this is why we want to have all three of those in our system, but we can't. We need to choose one of the. We need to choose the two of those. So, in other words, every distributed system must have a partition tolerance because it's built from a lot of computers or a lot of nodes in the system. So, we must have a partition tolerance, but we need to choose between consistency or to be a consistency or to be available for those systems. Now, what is a consensus? Now, before I'm continuing what is a consensus, I want to describe another situation. Let's say that you and a couple of your friends want to go to have something to eat. Now, everyone wants something else to eat. One of your friends even really don't like pizza. Really don't eat anything else. Now, what you can do to reach an agreement about what you're going to eat. So one option that you have is to flip a coin, but you can see the problem with the flip a coin. Now, with this option. The other one, you can go with the majority, but still, you have a friend who don't like pizza, and if everyone wants to eat a pizza, he won't eat it. So I want to tell you how Raft algorithm can help you to reach an agreement or consensus, even with this task of what getting to eat. So what is a consensus at all? Consensus is the task of getting all processes in a group to agree on some specific value. In our situation, is what we want to eat, even. So Raft. In the end, we reach what is Raft, right? So what is really Raft? So definitely Raft is a consensus algorithm, of course, but how does it really works, right? So Raft works with 3 server states. The first one is the follower. When a node is found itself in follower mode, it's going to be passive at all. You don't know what to do. You just wait for the leader to tell him what to do. Just like, please tell me what to do, I don't know anything. And you wait until he will hear something from this leader. Now, in the follower state, because it's passive, he have something that he have a timeout on this follower state. When the timeout runs only when you don't hear for a period of time, you don't hear from the leader. When this time's out, then we start the election. Like in the real life, we start an election, and this particular follower that times run is becoming a candidate. It will increase something that's called term. You can take the term as a time that divided between those elections. that we have. The candidate then will vote to himself first and send to everybody in the cluster. He will send, please vote for me. He increases term and say, I am the most up-to-date node in the cluster, and please choose for me. Now, only when you will get the majority of the votes from all the nodes, the majority of all the nodes that voted for him, only then he will become the leader, and then everybody else in the cluster will become his followers. And we'll wait for him to send some heartbeats to tell, hey, I'm here, everything is fine. Now, the leader is the leader when, in this state, he will choose how to do stuff. He will make the decisions, and this is how we can solve the consensus problem in Raft. Now, like I told you before, when a follower becomes a candidate, he will increase his term. So I want to elaborate about the terms and what they are. Now, the terms, you can take them as the time divided between those elections. Every time that a follower becomes a candidate, he will increase his term to say, I am now to divide himself from the post leader, and then he will send this term to the other nodes in the cluster, and in this way we can know that is in a different state, and is the most updated node that we can find in the cluster, and that's why we choose. Now, another key role of the terms is to identify absolute information. Sometimes we can have a problem that a leader is failing, the other leader is failing, and we choose a new leader. Now, okay, we choose a new leader, we increase the term, and then the old leader become available again, and he will send to you, to the nodes in the cluster, he will send them a message that say, hey, I'm here, but this is my term. This is my information that I want to give you. And because the nodes already increased their term from the oldest one, they will say to him, hey, please check your term because I think that you're not up to date and I can't receive your data again. So this is how we reach a safety environment, and safety environment of the cluster that does not have an old or unupdated data in the cluster. Now, so leader election. This is what happens. Like you can see, we have here 5 nodes. The black circles are the timeouts that we have on each node. When the time reach to its end, because no one here from the leader, like you can see here, all of the nodes start with term 1 in the start. Now, when here is S2, the node S2 is run out of the time because you don't hear from the leader, because in the start we don't have any leader in the cluster. He will vote for himself. You can see the black circle inside of it, and he will send to everybody in the node. He will send a vote request that say, hey, please choose for me. Please vote for me. Now, when everybody in the cluster will get this vote, say, okay, you are the most updated node that I can choose of. You're the first one that come to me, so I will vote for you. And then they will change their term to be the one that to be the same as the one that sent to them. And only when they will send to them, okay, I'm vote for you, only then he will become the leader of this cluster. And everybody else will become a follower and restart their timeout. you can see here, when the candidate become a leader because he had the majority of the majority votes of the nodes, he would then send an heartbeat every time to tell the nodes, hey, I'm here, and everything is fine. I'm still alive. And when the other nodes will get these heartbeats, then they will reset the timeout, and the process will start again. So this is how works the leader election. Now, sometimes if you ask, yes, sometimes 2 or 3 of the nodes, the timeouts runs together. So in this one, we call a split vote. We have here 4 nodes, A, B, C, and D. A and D runs out time together. They will become a candidate, increase the term, and send the vote messages to every node in the cluster. But what will happen if node C will get first the vote to D? He will vote for him because he's the first one. And node B will get a vote from node A and will vote for him first. Now, when a vote message comes to a node that already voted in this term, he said to him, I'm sorry, but I already voted for this particular term, and I can't. So every node can vote only once per term. So if he's already voted for this term, he can't vote it again. And then he will return to D, or then he will return to D or to A. You return to him, I'm sorry, I already voted. It's like real life. When you go to vote for a new president or a new mayor or something like this in your city, and suddenly you already voted, and suddenly the other candidate will come to your house and say, hey, please vote for me, I want to vote for me. What you can do, you say to him, I'm sorry, I already voted for this period of time. So what will happen here is that node A and node D won't get the majority of the nodes inside the cluster because they need 2 votes, two votes beside their own to become the leader. So what will happen then? They again will wait until the timeout runs. Here it's D. The D is the fastest one that runs out of time. And it will increase its term again and send again a vote message to say, now I'm turn 5. I'm more updated than the other one, than the state that I was. Please vote for me. And now we can vote. Now, this is a rare condition. Raft algorithm promises this will be rare algorithm because the time, or every time that the time reset is reset as a randomized between 1500 to 300 milliseconds. Just randomized between them. So one of the nodes will get eventually the less time and will be the fastest node that will become a candidate and a leader. So this is how Raft promise you that the split vote will become more rarely. Now, to make a safe system, Raft must save his data in a way, in some sort of a log. Now, what we can see here, we have 5 nodes, right? 5 logs to each of the nodes. When a request comes to the cluster, you reach the leader of the cluster. He will write this data in his nodes, uncommitted first, and we send to every node in the cluster. He will send to him this particular request. Now, the leader will commit his log only when he will get the majority of the nodes that tell him, okay, I have this data in my log. like this. Then they will send to the leader. They will send him that, okay, we will got this. We will write our log. In our log, we will write your request. It can be whenever you want. We can take like add 5, -7. This is the request for the client. We don't know what, but they must do it because they follow of the leader. When the leader will get the majority of the nodes that tell them, okay, we write everything to our log, only then he will commit his log and send it to the client. Let's say, okay, this is the data. I saved the data in my log. Now, the data that's inside the log must be in the same order that is come. So when a leader will send his request to the other nodes, always he will send it as the order that will come. It must have in the same order. Yeah. So after that, the leader commit his changes in the log. He will send a message to everybody else with the heartbeat that says, okay, I committed it. Everybody else can commit it too in the cluster. Now, I want to show you some practical examples. 1 second. Okay. So here what we can see is the same thing that I showed you before. We have 5 nodes that waited for the leader because we don't have a leader, so they have timeouts. And we can wait for a timeout, just timeout one of the leaders. And we can see that he will send a request to everybody else in the cluster and say, please vote for me. And they will say, okay, I will vote for you because you are the first one that come to me with increased term. And then he will become the leader of this cluster, like this. And you can see that he will send them again after a couple of times. He will send them again an heartbeat. They will reset the timeout, and again and again and again. Now, let's say, that we send a lot of requests. Something in the cluster. Like you can see, he will send it as the same order he got those requests. And after the all committed, we can say that our cluster right now is up to date and have all his log application as safe as he could. Now, what happens when the leader dies? The leader dies, and let's say another node dies too. And then we have only 3 nodes in the cluster, so that's fine, because we still have the majority. And then we choose another leader. Like now we have a split vote. So we need to wait. Just a minute, sorry. He increases term again, and then we become the leader. Now, if we're doing a request for this now, and you have a different log, like you can see. So the other 2 nodes don't even know about the changes that come in the log because we have a different request right now in the logs. When I return the leader right now, it will still be in term 2, but then the leader 4 will send him heartbeat with his log. And when the other leader, the older one, will see that he have less term than the other one, because he was in 2 and he was 4, he will then go to check his log, and we see that, oh, I'm not up to date, so you are going to be the leader, and I'm going to be your follower. The same as the other one. If we return it, he will get an heartbeat from the leader that say, hey, I'm in term 4, and this is my log. Please take all the things that I want to take. And this is, it will be faster than I should, but fine. This is how Raft works. This is how we make in distributed system and take the democracy, the voting, and the election for computer science. And this is how Raft can help us to achieve a consensus and to achieve a safety and reliable system in a cluster or in a distributed system. Okay, just a minute. Now, okay. So, everything is fine. The Raft works. Raft make all the decision because he have a leader and he have the followers that come to him. But what is our job in all of this? I just want to illustrate that this is from our studio in RavenDB, right? It's just that how Raft looks like in RavenDB. So here you have a leader, and 3 of the nodes are the members, are the followers. Now, what Reda's job in all of this is really to make the request, like create a database, create an index, or just add some data or something like this. So this is really our job, because Raft take us to a place that we don't need to worry about the agreement about the values that we sent, because we have the leader and we have the followers that must listen to the leader. Now, let's show you about this is what happens when, let's say that a node fell down, right? But we still have the majority of the nodes in the cluster. So everything still works because we still need to be fault tolerance, and everything works fine. You can see here that we can't fail to connect with B. B is fail. Now, what happens when the leader fell down? Again, like I showed you before, the leader is out. We choose another leader, but we still here have the majority of the nodes that can't work. So B will get the majority of the vote from C, because we have only 3 votes, only 3 nodes, and it will become the leader, and everything will work fine. Now, what happens when the majority of the nodes fail? Like here, A and B failed, and then only C left. Yeah, the timeout will run out in C, and C will try to vote himself and send to the other nodes, please vote for me. But he can't get the majority of the nodes. So only in this situation we can stop working, and we need to go and fix our cluster. So this is why we don't advise to make a 3 nodes cluster, because the possibility of 2 nodes to fail is much higher. So for 5 and up, it's fine, but 3 is a little bit problematic. And of course, when all the nodes come back, the cluster will be good again, and everything will work fine. We don't need to worry about anything else. Okay. Questions? Anyone?
The nice thing of you have a lot of time to questions. This is a complex subject, so
yeah.
Probably, please, one question.
Yeah.
This guy comes from Israel, so let's use his knowledge.
So, nice talk. Regarding Internet Explorer or Google Chrome that you present us, could you back there to be more easy?
Where here?
Yeah, no. On the web browser, the Edge. Yeah.
This
yeah,
one,
the animation
demo.
one. Yeah.
Okay.
So you explain how the election works, right?
Yeah.
So when the login are replicating, what happened if one down,
yeah,
and then another one that was down come back? Because you will have a mess regarding the logs, no?
Okay, understand. So we say if, let's say that we kill the leader, right?
Yeah, and kill S2, for example, 2.
Okay, so we kill the leader and we kill another one. Another one to kill?
No, it's okay. And you start to the election, right?
Yeah.
Like you
We
said.
will now wait for the timer to run. Let's do faster things. Sorry, just a moment. The term will increased. And we choose to be the leader. Yeah.
So if you start sending requests through the S4, the new leader,
A new leader we want?
yeah, it starts to send a request.
Okay. Send to request. All right.
Actually, probably a bunch, right? More two, please. More two requests, please.
More to request.
Yeah, because when you bring back S3 and starting replication, you will kill the master and the S2 will be back. And then S3 dies. It's
You have
crazy
more,
complex, right?
Right? Yeah. Now what? Yeah.
Now S3 come back.
S3
S2
come back. Okay.
But probably you need to go a little slow, right? And then when the replication starts for the S4 to S3, you should kill S4, probably S3 won't be a leader, right? Because he does not have all the data, right?
Okay. Kill this one, yeah. Sorry, just, no. So let's start from beginning. It's hard because I don't have a mouse right here. So let's do something like this. Again, let's time out, be the leader, right?
Yep.
Now have stop 2 of them. Take the leader in this one. Time out. And then have 3 or 4 more requests.
Yeah.
Okay. And then what?
And then this one will go down, and the first S2 will become up again, right?
Okay.
So it
And
starts
then
receiving.
F3 will stop.
Yeah. And then S1 became up. That's
Okay, I understand your question. Okay. Okay, so
This is the most complex
There is-
question that
no,
I have ever
okay,
seen
there
in
is-
the QCOM.
okay. There is another
Congratulations, man.
listen a minute, there's another state when we do a log application. Even if our term is bigger, but our log is not updated, up to date, I will check only when my term is less than you, I will check if you can become a leader. But first, I will go to the log and check if your log is more updated than me. If not, I will send you a request. I'm sorry, I can't give you to be the leader because your log is less updated than me. And then you will wait until another node will come that have the most updated log in his system. And then he will become and then the other one will eventually become the leader, and all the log will be updated to what they needed to. Another one question?
More questions? Oh, good. There and there. You've asked to stop and continue and resume. And
Yeah.
Yeah, hi. No, the question was, well, it's probably more related to how RavenDB deals with the scenario where, well, was pretty much your last slide, where when you have only one node left on the cluster, so it can't promote itself because
It can't promote itself.
Yeah, it doesn't have the majority.
Right.
But speaking of Raven particularly, and maybe you can say about how Raft deals with that situation,
All right.
does that mean that the cluster is offline or the cluster,
cluster is
down?
dead.
Is dead.
Yes, only in this situation the cluster is dead. You don't have the majority of the votes. You don't have the majority of anything.
So you won't answer.
I'll give you another example of something. I can't show you because I don't have it, but let's work our brain and see what I see, right? Let's say that we have those 5 nodes, right? And the leader is S4 right now. Then we have a network partition that kill the line between S4 to S5, S1, and S2. and S3 is with the S4 with the network partition. Now, S4 is the leader, right? But it can't get the majority of the votes. It can't get the majority of the votes because you only have S3 to return him, okay, I have this. Now, S5, S1, and S2 will choose another leader because they don't going to hear anything from the leader, right? Now, because they have the majority of the nodes, then they will become the leader. One of them will become the leader and start to sending heartbeats, and the term will be increased and stuff like this. Now, let's say that you have two clients. One will send to the S5, S1, or S2 a request, right? Because they have the majority of the nodes, they can still work and log and just put the data in their log application. I'm sorry. But let's say that another client comes and sends a request to S4 because he's the leader, but he can't talk to another one. Now, he will get this request and try to send it to majority of the nodes in the cluster. But he can't have the majority that said to him, okay, I'm write down this particular request in my log. So his log will stay uncommitted. Now, if we fix this partition, if we fix it, and let's say that the S4 will try to send to the other one, hey, this is my request, but the other one have a different term than the other one, a greater term than his, or not a greater term, but they have more updated log than his because he has uncommitted changes in his log, and they have committed because they can reach the majority of the cluster. And then what will happen is that S4 will say, okay, I can't be the leader anymore, so I will take the log from you, and he will delete every uncommitted change in his log. And we start to update his log for the other one. The other meta request, and eventually, he won't get any response from the server because the server won't get any of the majority of the nodes to tell him that everything is fine. So you will wait. So the most problematic states in cluster at all, not just in RavenDB, it's just when you don't have the majority of the votes to vote, to be elected, or just to send you, okay, I have this. And we're doing this to solve the consensus problem, to be more safety. We need a majority that wrote, because if something happens to me, the majority of the nodes still have this data. And then can, again, choose something and everything will be fine. Now, another thing, let's say that we are right here and we have uncommitted changes in our log. And then another leader will come. He have the same log as ours, the same one. And he will increase his term to 4, like is his, and he have another request. And then I come back. I still have uncommitted changes, but I have a request in higher term. When I get this log, I can, because the leader have the same log as I am, like 3, 3, 3, 3, and then 4, I can then commit my changes, commit the 3, without get the majority, because if higher term than me committed the changes, so I'm pretty sure that the other state that I was is already committed. So this is another issue that you can solve by doing the log application. Another question? Yeah.
About Raft and RavenDB. What if one node is stopped and then database creation operation is executed? How is it going to be executed afterwards, after the node restarts?
Just a minute, I'm sorry. What?
A database creation.
Yeah, you have a database creation.
Okay, a node is stopped.
Node is stopped. Yeah.
And then, so it will be stored. Where would it be stored?
Okay.
Because
I explained it outside in the booth, but how can I answer something like this? Is something. RavenDB works in 2 layers, right? you're working on the cluster layer for create a database or create an index for this issue. And in the other layer is work on the database layer. Now, in the Raft layer, we're choosing to be consistent. Why? Because when you create a database or create an index, you want it to be in all your cluster. Everybody needs to know, so you need to wait to be the most updated at the moment. Now, when I send you to write something in your database, and let's say that another user will come to me and request this data, I can give him something. I need to be available. I just think we have them. It's not needed to be the most updated, or only if the client wanted it to be the most updated, like any news websites. When you enter a website with news, you not always get the most recent article that someone wrote. Now, your question is, what happens if a node is outside and we have created a database right now, and we can send it to have this database? So if we have the majority of the nodes, everything will be fine, right? Because we can still write a database to the majority of the nodes. And when these particular nodes will come out, then the leader will see that it comes out, and it will send it, hey, update yourself now. This is my log. We have this sort of request that you need to do right now, and please update yourself. And with update, and everything will be fine. Now, another option that you have in RavenDB is something that you can choose how much nodes have this particular database. Like, if I have, let's say, 5 nodes in the cluster, the leader can choose, okay, S5 and S4 will have these 2 particular database, and S3 and S2 will have another database. Now, all that nodes knows about those database, and if I request S5 about data that can be found in S2, it will know that it's there, and will just send the request to the leader, and the leader will say to S2, okay, bring me what I need. Now, if S4, let's say, for example, is down, and the leader see that it's down for a long period of time, you say, okay, I only have this database on one node, and I can replicate it on another one, because I need 2. But this is something that you can choose. It's very optimized for you what you want to do, because it's taking time to replicate it everything.
Okay,
I answer your question, it's fine?
É importante, eu trabalho na mesma empresa que ele, tá? E eu posso responder essas questões também em português, se você tiver depois mais questões sobre esse aspecto em especial. Ok? I said that I can help him as well.
Okay.
Not like you, but I can
He
provide.
can ask you, and you can ask me, right?
Yeah, for example.
And then you can translate it, and everything will be
Okay,
fine.
perfect. Mais alguém? Ok.
Yeah.
Hora do gordinho correr.
Yeah, just for curiosity, how does communication work? Like, you use a specific protocol, or like HTTP, or a different protocol? And
Communication between
Yeah.
those two
Yeah.
nodes? Okay, so the communication work of HTTP requests, regular HTTP request, REST, individual, and you have sometimes the TCP request between them, but it's really up to you to do it. But in Raft algorithm, they can only send messages by network. That's it. Okay?
Ok. Mais perguntas?
I'm ready to another question. Yeah.
Ok. Temos.
About everything. Yeah.
It's most related to design of RavenDB. There are other consensus protocols, of course.
Yeah.
Is there any specific property of Raft compared to PAX or something like that to better understand the choice of Raft for RavenDB?
Okay. So why we are using Raft? We're using Raft in RavenDB only for the basic, that we have a leader, we have the followers, and for your systems, you can take this idea of the Raft, of the democracy that happens, that solves you this particular consensus algorithm, this consensus problem, and to add anything that you want. Like I told you that we have 2 layers of database and the Raft and the cluster. Now, Paxos, like you said, yeah, it was to a consensus algorithm, but it was so hard to understand that someone said once that I read that only 5 people in the planet knows really good how Paxos works. So Raft algorithm became something that said, we want to make a code that everyone can understand. Like in 25 minutes that I've been here, I hope that all you understand what is the basic of Raft, how it works, and how it's log application. Of course, that you have a lot of states that I didn't tell you, but you can go and research about it because you have a lot about the logs that happens. So we're taking this Raft, to be more understandable. Everybody needs to understand, and eventually, because sometimes you have a code, you come and develop something, and you come back after 1 year, and you say, "Damn, I don't understand anything." You know, I once saw a comment in a code that said, when I wrote this code, only me and God knows what the code does. Right now, only God knows. So if you don't understand anything, just continue to another developer. So it's really important to do, when you develop a system, to do it more understandable, because if someone comes after you, he must be understand. Anyone?
One more question. We have space for one more question. Time, not space. Time for one more question. No? So, thank you very much.
Thank you very much. I was Dam Chaim Shalom. Thank you.